yeah, it's essentially, as already mentioned in the introduction, I am still very much involved as a senior scientist at university, but I also have the industry part, which is really nice because there I can sort of do fundamental research at university and then try out some cool things at Emmi and apply this to real world, like real relevant problems. So for the goal of this talk today, I first want to talk a bit about AI for engineering, which is sort of AI beyond large language models. So I actually really liked how the talks sort of evolved today, because we've been hearing lots of large language models, and the more actually we got to my talk, the more it was actually more about PDs, numerical simulations, and this is essentially what we understand on AI for engineering, and I will talk a bit about the differences, what we have when we use large language models, for example, as compared to AI for engineering, and why I believe that AI for engineering is essentially fundamentally harder than just LLMs. Then I will actually sort of do a brief detour on stuff that I am working on at university, which are neural surrogates for nuclear fusion. And then I will come back from fusion to Linz, to our startup Emmi.AI, and explain a bit about what we're about and show some cool use cases and projects that we've been working on in the recent history. So from a research perspective, if you go to the main research conference, which is called NeurIPS, then you see that a vast majority of the research is actually dominated by large language models right now, and rightfully so, because they are incredibly useful and are really nice tools and open up really nice use cases. And well, if you look away from language model accepted papers, then focus is usually on something like image processing, computer vision, video processing. And there is this, in recent years, it's sort of, there's like a community sort of has developed with the consensus that, if we just build things bigger and bigger, then at the end, at some point, we'll get to intelligence. And here I'm actually including this photo of Ilya Sutskever, which was one of the original founders of OpenAI. He was holding a keynote at last year's NeurIPS, and what he was saying here was, essentially what has enabled this era of scaling is, because we have the whole internet and we just scrape the whole internet and have terabytes of data and just throw this into our machine learning models, and we get, really nice tools out of it. But well, at some point, we just use up all of the internet, and then where do we get our data from? And I think this is a very, very nice point to sort of highlight the difference between AI for engineering and AI for other disciplines. Because in engineering, we are not yet at this, we're approaching this era of scaling, but we're not quite there yet, simply because, we don't have this internet of, numerical simulations. Usually, these engineering simulations are very, very expensive. They're very costly. We need tons and tons of supercomputers to, compute things and approximate things. And usually, companies are very focused on specific use cases, and then they have a lot of data at hand for that particular use case. But it's not that they would just openly make everything publicly available of their data, because their data is essentially their intellectual property. And what we find is that machine learning workflows are usually what is the missing ingredient from a company perspective to really sort of scale things up. And we've heard already that this data is the oil of engineering might not be the best way to put it, because you don't throw away data. But there is actually some cases, I will actually come to one of these cases later, where engineers are actually forced to throw away their data because they simply cannot handle the vast amounts of it. So maybe in some sense, it still is related to oil. Right, so this is actually very much in line, I think, with what a lot of people have talked about today already. Essentially that there is an increasing importance in energy supply. So this prediction right on top there is actually not coming from myself, but it's sort of what I pretty much agree on in the next 5 years. AI breakthroughs, they will probably still be based on some sort of transformer or maybe the new XLSTM, but they will still probably be built or run on NVIDIA GPUs, which are built at TSMC with ASML machines. But what they actually use for building GPUs is actually technologies that come from Europe, which is nice. So we've heard already in the morning that Infineon powers NVIDIA GPUs, and there's other companies in Europe that Europe still has a say and still sort of has a say in where this will all lead. And there's currently this trend that lots and lots of the big players are just pouring money into GPU centers with like hundreds of thousands of GPUs, which means that we will need more and more energy in the future. And we've seen these nice charts in the morning already. And this is sort of mirrored in for example, if you look at the stock market, like the share prices of Siemens Energy, for example, which has skyrocketed in the last year. And then also when you look where money is being invested, so there is, for example, startups that work in nuclear fusion. So there's this one German one, which is Proxima Fusion, which raised like a huge ton of money for building stellarator-based fusion power. And then there's, for example, the UK Atomic Energy Authority, which is also investing like crazy because this is essentially, like whoever really makes this work has, sort of won this game. And this is actually a nice point to go to show an example of where we've been applying AI to at university and where AI can lead to real disruption. And this is, essentially nuclear fusion. So ever since I started my position as a senior scientist, I've been sort of involved in this collaboration between the JKU and the UK Atomic Energy Authority. So they are currently building their next generation tokamak reactors. I'm going to show some pictures of those in a bit. And that's pretty much what I've been focusing on for the past year. So I'm not sure if everybody here is familiar with the terminology of neural surrogates. So just going to briefly explain it. Surrogates are essentially emulators, and they can act as a plug-in replacement for costly simulations. And well, the real benefit of them is if you're able to get such a neural surrogate to emulate the simulation well, then you have real benefits in terms of optimization cycles, better designs, and this is sort of what we call engineering 2.0. And what this ultimately enables is digital twins, where you can do real-time monitoring and real-time decision-making, which is especially important for nuclear fusion, for example. And particularly in this domain, I think like one of the most important things and the new frontiers that sort of AI will unlock here is optimizing reactors based on certain optimizer parameters, operating parameters, and then also actually being able for like researchers or practitioners being able to handle the vast amounts of data that is being generated. So, what is nuclear fusion? So, I've mentioned the tokamak reactor before. It's those donut-shaped reactors that you see here. Essentially, how this works, or the motivation there, is to produce energy by fusing hydrogen isotopes. And for this, you essentially, for ions to fuse, you need to overcome very, very strong forces, the Coulomb forces. And for that, this reaction needs to happen in a plasma. A plasma is essentially nothing other than an ionized gas. And in this donut-shaped reactor, you would have a plasma that is being heated up to hundreds of millions of degrees. And then you pump ions and electrons in there, and then, those circle around the donut here, and then at some point, two isotopes or two ions will merge and then release energy, and then create some side products and lots of energy. And so the problem here in nuclear fusion is that this plasma, because it is so hot, there's no material on Earth that could really confine it. So what we need to do is we need to sort of strap those coils around the reactor to induce a magnetic field, which then confines the plasma. And I'm going to bring some examples here why fusion needs AI. And one point is there's an immense volume of data, and it's not just any data, it's really complex data. So I'm going to show you some examples in a bit, but the data is very high dimensional, spans across multiple scales and modalities. And usually when you talk to a plasma physicist, if they simulate what's going on in the plasma just for a few seconds, you can exceed like hundreds of terabytes of storage requirements, which is why they usually simply throw away all of the data and just keep integrated downstream quantities. And this is one point where we actually already have a work, which I'm going to show later, but where AI can sort of really enable practitioners to enable new scientific discoveries by actually being able to store these amounts of data and being able to analyze them post hoc. Then there's lots of transfer learning opportunities. So usually it's the case, like almost with any other numeric simulation, it's the case that you can, for toy settings, you can produce lots of data, and they are not really that expensive because you have a coarse resolution of your mesh. And but then the thing is, you can generate lots of data, but they don't capture, if your goal is to capture fine-grained turbulence, then you will need more expensive data. But there is usually some sort of positive transfer between coarse resolution and finer resolutions, which means that you can leverage those coarser resolutions to actually get better models on the finer resolutions. Right, and then compute and infrastructure demands. So there is already some research on AI models in this realm, but they are very limited in scope. The current numerics, if you really go to the, even if you only simulate the core of this plasma with all the ingredients, then this can, for a single simulation, already take weeks on a supercomputer, which is insane. And this is really where you can get benefits with the amortizing cost of AI. So there will be lots of time being spent into development of these models and training of these models. But then once you have this model and you're sure that it actually accurately represents what you're interested in, then inference just usually is in the order of seconds. And then you can simulate lots of data, and then you can also search through a very high dimensional parameter spaces, which can then ultimately get you to the next stage of performance. And there was this actually really nice example from Google DeepMind, which was a few years ago, where they used reinforcement learning to control the shape of a plasma in here. And this is essentially just a primer on what will come in this direction, because for this setup, to actually be able to control this, you first need a simulator. And to get a simulator, you need numerics, and this is essentially where AI can really have an impact there. Right, so why is it what's the problem actually in fusion? And why do we need to simulate how the plasma behaves? The reason is turbulence. So, well, in plasma, we heat it up, and usually just naturally there arise some turbulence behavior because of microinstabilities. And those microinstabilities accumulate over time, and then you can get like really crazy turbulence in there. And what this turbulence causes is essentially particles, momentum energy in the form of heat to transport from the core of the plasma towards the reactor wall. And as you can imagine, this is bad, because if you have like hundreds of millions of degrees being thrown at your reactor wall, it will break at some point. So yeah, it is really essential for power plant design to simulate how the plasma is going to behave. And yeah, I was actually hoping that I would be the first today to show some PDEs, but unfortunately I wasn't. Yeah, how do you model plasma turbulence? Essentially, you model it via this framework of what's being called nonlinear gyrokinetics. And what this is doing is essentially evolving a 5D distribution function. It's 5-dimensional because it is not sufficient to simulate at what position a particle is in the tokamak, but it's also essential to know what velocity it is traveling with in each direction at this position. So this usually, if you consider 3-dimensional positions, this would actually get you to a 6-dimensional space, but this is exactly what gyrokinetics is doing. It does some approximation so that one of these dimensions gets lost, because otherwise it would just be even more crazy. And yeah, as I already mentioned multiple times now, this like simulating this in all of its beauty can take like a huge amount of time and compute. And so what practitioners usually do is that they take this huge equation here and they break it down in different parts. And then they have, for example, this linear part here and this nonlinear part here. And this nonlinear one is actually the one that results, or that, yeah, results in the most computational requirements. So what do? They just say, okay, let's just not compute this. Then, well, on the linear part, it's still 5-dimensional. 5 dimensions are expensive. Okay, why don't we just do 3 dimensions and solve hundreds of 3-dimensional equations? It's still faster than 5 dimensions. Okay, we get an approximation, and yeah, that's what we do. And yeah, this is essentially can also be, so they usually term this reduced order modeling, and you can imagine that simply by just throwing away stuff or splitting up stuff, you just lose lots of information. And well, if you now just think about how does 5D data actually look like? I'm not sure if any of you can think in 5D. I cannot. So you need different ways of visualizing it. So if you roll out this equation that I've shown in the last slide, you will end up with some sort of fields, 5-dimensional fields, where you have 2 velocity dimensions, which are these 2 here, and then you have 3 spatial dimensions. And well, just for visualizing purposes, what you can do is you can simply take sort of planes in this 5D field, slice it, like take those slices out and visualize those. The way we like to think about it is that you have this plane of velocities, and then at each velocity, you essentially intrinsically have a 3D torus where, you know, depending on the current velocity coordinates, you have some turbulence occurring or not. Okay, this is, yeah, okay. Right, so I already said that with numerics, it's pretty much impossible to actually model these 5-dimensional fields. That's why they use these numeric approximations. So what we did at university is we actually developed a deep learning system with which we are able to simulate 5-dimensional nonlinear gyrokinetics. And well, this is work that I've been doing with a PhD student of our lab, and we focused on this very toy setting in this field, which is just 6 terabytes of data. And then we trained this model to not only predict this 5D distribution function, so this 5D fields, but also sort of downstream quantities that you would usually derive of this 5D field. This is sort of a soft constraint for the model to adhere to certain physics, because we know that a certain 5D field, you would do some crazy integration over this field, and then you would get first potential fields if you integrate over velocity space, and if you integrate everything out, then you essentially get heat and particle transport from the core to the reactor wall. And we just add those as essentially soft constraints to the optimization procedure. And the cool thing with deep learning is if you have control over the architecture, you can always bake in some inductive biases. Biases that will sort of steer your model to certain parts of the physics. So we know, for example, that a certain mode in the 5D field corresponds to a certain nonlinear physics that I will show in a minute. And what we did there is we slightly tweaked the architecture to just give this one mode a lot more importance, which in turn results in the model much better capturing these phenomena. Right, and now if we take this model and we just roll it out in time, so usually it's trained by predicting always the next time step, and we now take it and just roll it out in time for, 100 time steps. You always have these sliced planes here in different combinations of axes, and the predicted versus the ground truth. Then, well, you see, okay, it sort of looks all right, especially if you look at the spatial coordinates, which is good because this is where most of the turbulence comes from. And then you have these. The more you roll this out, the more you have sort of deviate, especially in this velocity space here, which is just a very, very common shortcoming of the way some of these neural surrogates are being designed, which is in an autoregressive manner, which is actually what each and every language model is doing. And for language models, it works pretty well. But for these kinds of data, especially when you have chaotic systems, it's actually, it's more meaningful to view this through the lens of generative modeling instead of deterministic modeling. But still, it is pretty remarkable that we can just roll this out for 100 time steps, and it is pretty much stable. And what I mentioned earlier, a few slides earlier, is that neural surrogates will give us the capability, will essentially unlock new capabilities. And one of which is, for example, in our case, that we can now look at nonlinear physics. So there is a certain 5D phenomenon which controls turbulence, which is called zonal flows. And it's actually, when you look at the surface of Jupiter, it's actually the reason why you have this sort of this oscillating pattern on the surface, because these are essentially different wind speeds that blow into different directions. And these are just another instance of zonal flows. And you pretty much have the same behavior in a plasma. And the zonal flows control how much turbulence will evolve. So you can imagine that they are really important to turbulence modeling. And when we now compare or see what our gyroswing is predicting versus the ground truth zonal flow profile, then we can see, okay, this is actually something that is that matches pretty well. And this is just something that you cannot do with these reduced numerics models, because they entirely neglect this. This is in the one term of the equation that they just throw away. So yeah, just to summarize, what we did in this work is, we built a scalable, efficient and stable neural surrogate for plasma turbulence modeling. It will definitely not be the last instance of this model, because this has been, as I said, a toy setting essentially. And there is a lot more work to come, but it's already pretty remarkable that we actually made this to work. And the scalable aspect will actually come back later when I talk a bit more about what we're doing at Emmi.AI, because this is the main focus, that we are trying to build things that are scalable. Now, I also mentioned that compression is an important part in plasma physics, and well, a PhD student that I'm working with built this, sort of investigated how you could essentially compress all this data on the fly, which means that you don't need to throw it away. And neural compression methods essentially scale a lot better than their traditional counterparts. And the good thing, so this is actually, you can see this at this region here. So these are neural methods and the other ones are traditional ones. And the really cool thing is that for neural methods, you can also, again, add these soft constraints such that they adhere to different physics and can reproduce those. And especially if you then look at the scaling curves for physics on physics quantities, then with the neural compression methods, you're just way better off than for any other compression that you can imagine. And you can actually steer this into like almost hundreds of thousand times compression ratio, which is also something that is very difficult to do with traditional compression. Okay, so I've covered the easy part. Now let's go to the hard part. Let's go back to Emmi.AI and to Linz. Yeah, so I just recently joined Emmi.AI, and yeah, it has been founded in the beginning of this year by Dennis, Mix, and Johannes. So Johannes is my supervisor at university. He's leading the AI for Physics simulation group, and yeah, currently we are actually pretty rapidly growing at the moment. So we currently have 25 employees, the headquarters in Linz, but we're currently expanding to Paris, Oxford, and the US. What is pretty nice is that we received a huge seed funding round, which essentially was the highest round ever in Austria. And I just read another a post on LinkedIn earlier today where companies were listed based on the amount of money they raised in Spain. And there it was actually 6 companies that raised more than what we raised in our seed funding. But this was actually not seed funding round for them. So yeah, there is, there is some investment, but yeah, we think it should be more, especially comparing to US companies. In the US, it's usually you just throw out an idea and they just throw money at you. In Europe, it's a bit different. And if you look at a comparison to the highest spin-out university value, like university spin-out value, then well, the big players there really are the UK and Switzerland. And there's lots of France is really well represented, in Germany as well. Yeah, I will not ask you to look for Austria in there because we will run out of time then. But yeah, this is just to sort of illustrate a bit or show you a bit the startup scene and the situation in Austria. So the partners that we're currently working with are Siemens Energy, Simcom. We just recently partnered with the Formula One team. There is an ongoing collaboration with NVIDIA and potentially also the UK government. So what we are doing at Emmi, what's our philosophy? So we are interested in scaling, and in particular, scaling machine learning models to very large-scale problems where you usually need numerics that is extremely expensive. And some examples for those are, as I already mentioned, Formula One, where you usually do some form of computational fluid dynamics with billions of mesh cells in 3D. Yeah, those are usually non-transient, but still it's a huge computational burden, especially if you want to resolve all the fine-grained turbulence. And this is where these are systems where AI can really lead to a disruption there and change the way of how we're approaching these problems. Another example are these fluidized beds. So this is a method that has come out of Emmi and has just recently been published at Nature, which is essentially coupled fluid dynamics and discrete element methods, where you have like hundreds of thousands of mesh cells and then a few hundred of thousands of particles and coupled interactions and transient over time, and you need to simulate, which you can imagine is extremely expensive in a numerics way, but with machine learning you can speed this up. And essentially the way we see this is that there's 3 different axes of scale. One is model scale, which is, well, I would say pretty much solved because we do have huge models already. We know how to scale transformers. We know how we can make them larger, what stabilities or instabilities arises if we do so. There we have a lot of experience from the language modeling domain, fortunately, which we can transfer over. Then the 2 other axes here is data scale and problem scale. And at Emmi, we're laying particularly focus at the problem scale, but also on the data scale. So with respect to the problem scale, we need to build scalable frameworks, sort of making machine learning models scalable to these huge complex problems such that they can ingest billions of mesh cells if needed. And there's actually quite a lot of works that came out of Emmi, actually before I joined Emmi, but it's really good works. Essentially trying to converge on a framework which sort of universally works well across different types of simulations, where you really go to large scales. And the latest one, the ABUPT model, is something that we, for example, used for airplane simulations, for car simulations, for discrete element methods, for all sorts of different problems. And it actually turns out to work pretty well. And it is also, if you compare it to baselines in the machine learning sense, then you usually get a lot better, a lot more scalable behavior. And another problem that we're recently laying a bit more focus on is data scale. So since here we are actually restricted at in numerics, like how we spend our compute. So we imagine that you have a certain amount of compute that you can spend. We need to understand how should we allocate this compute into different resolutions, for example, different meshing, to essentially get a neural surrogate that gives you the best performance. And yeah, we just have a recent paper that we'll present at this year's NeurIPS conference, where we essentially investigate a similar problem in aerodynamics when you go to transonic regimes, where you really have like turbulence and shock waves on the wings, and tried our surrogate methods, and it actually turns out that they work pretty well on those. And yeah, now to just some more, we'll just briefly go over these other success stories that we had. So we were essentially, with Siemens Energy, sort of building a digital twin for transformer winding simulations, which is a pretty cool topic and was very successful. Another thing that we were looking into is essentially crash testing with Renault. So for crash testing, you would have some sort of assembly on top of your car, and then you drive against an obstacle, and then you would simulate how much this assembly deforms. And well, as you can see, with our surrogates, we can pretty much replicate this, which gives you a huge speed up in how many different configurations, velocities, whatnot you could simulate. Then we have a recent collaboration with Luminary Cloud, which will be published soon, where we apply our surrogate models to simulations on whole airplanes and different types of cars. And another example is actually with SimCon. So there we're sort of trying to build a foundation model for injection molding. So what's the use case here is that you have various geometries, and you would inject some welding material in there, and you want to simulate how this distributes and at what points you get what pressure when you inject this material. And there we actually had also made some quite a good progress that our neural surrogates can really transfer across different geometries and simulate this really well. Right. So I was actually thinking that I would have taken more time already. But I will talk about the takeaways. What I think are the takeaways for this presentation. So I very strongly believe that AI will disrupt the landscape of large-scale engineering disciplines. And I think this disruption has begun already, even though it is a pretty slow start. So it will take lots of time. It will take a lot more research to really figure out how to best do things. And it will just take some more time. It's also going to be the case that lots of numerics will be ported to GPUs. So not only the machine learning models will run on GPUs, but also numerics will run on GPUs. And this has partly already happened, especially in disciplines which are otherwise really crazy, infeasible, essentially, to simulate. And this will also facilitate, then again, the building of neural surrogates, because then you have, with better numerics, you get a better data to train on, and this whole cycle gets sped up, essentially. And another point that I think is very much true is that we will sort of need to rethink the term foundation model when it comes to AI for engineering, because it essentially is not the same as for language modeling, where you just have essentially all the data that is out there and train your model on this, and then you have your foundation model, which transfers really well to almost any task that you can think about. But here it's really you don't have all the data publicly available, and usually if you change the physics a lot, then it's questionable how much you can actually transfer from one system to another one. And so, especially since the bottleneck is in the data that we need for training those models, I think it will take some sort of a redefinition of the term foundation model when it comes to AI for engineering. With that, I am essentially at the end of my talk. Thank you for your attention.
Thanks for the very nice talk. And let me open with a very provocative question and hear your take. So what is Austria in terms of startup, especially in AI, startup culture, doing wrong? What is UK and other countries doing right?
That is a very good question. This is that's a really good question. I think
it's not provocative towards you, but provocative towards Austria, because I completely agree. So I don't wonder that Austria was not even showing up on this list. So
I think that. So in my view, I think that it first comes with a I don't remember what the term is called, but prestige. So prestigious universities, if you look at that list, this one here, then usually where you have the most spin-out value of a university are the most prestigious ones, right? So you have Oxford and ETH, which are like worldwide. I think if you look at the university rankings, definitely one of the they're in the top, which is, I think, what definitely contributes to sort of them being seen seemingly more credible. And then, in Austria, there's, I think, generally the problem with funding. So I'm not sure. At least was a few. So I just know it from our lab. So Sepp, the head of our lab, is usually very open that we lack a lot of funding. And if you look at universities, for example, especially in Switzerland, at EPFL, for example, they get funding to build their own tokamak reactor, where they can do experimental stuff, which allows them to do interdisciplinary research where startups can form. For us, we really lack this funding. So there's also, I think there's also a lack of industry around university in general. So if you look at those places where you have lots of startups, and ETH at Zurich, you have lots of the big tech companies, right? And there's a huge talent pool, and there's lots of motivation for those people there to form startups then. That's essentially my very limited take, being 3 months in a startup.
More questions? Or provocative statements?
Hi. How important do you think uncertainty quantification is, and what kind of methods, if any, do you guys use for uncertainty quantification in your simulations?
Very important. So, I think we've seen that there is, in general, if you look at the language model research, there's lots and lots of focus now on uncertainty quantification. And I mean, in engineering, it's, especially if you're doing a simulator or a digital twin, I think it's a lot more important there, because you need to make sure that at least under in a certain range, you are there, right? And especially when it then comes to, let's again take fusion as an example. If you just simulate something wrongly and miss a heat shock or something that completely destroys your reactor, well, then you need to rebuild a reactor, which can take, I don't know, I mean, it's quite quickly nowadays, 30 years or so. So, there's a huge work to be done there. There is some techniques, though, or some modeling frameworks, let's put it that way, that sort of can give you some uncertainty estimates already. So this is more going towards, if you model things in a probabilistic sense with, for example, if you use diffusion models for turbulence modeling, then you can actually sample from this diffusion model, which gives you sort of an estimate on uncertainty. That's where we'll see a lot more about, and I think it's probably even more important than in language processing.
So Axel Bolleres, University of Economics and Business. Maybe with that hat on. So you mentioned the surrogate models as having applications mostly in engineering domain, replacing traditional simulation techniques in a sense, right? So, I mean, simulation is also used a lot in business and economics scenarios. Are you working towards this area as well, or do you see applications there?
So we in particular are not working towards that. I mean, I think it can have a place there. I think it's about finding the proper use cases, probably. I mean,
the latest or media example was epidemic simulations, of course, right? So, for instance, spreads and factors like mobility. When we remember a couple of years ago, so this was mostly done with simulation techniques, right?
Yeah. This is, that's actually a very good point. I think that there's, I think it probably depends a bit on how much data, because those are things where I'm not sure it is that easy to generate data. Like if you take pandemics, how many pandemics, like should we simulate a pandemic now to get more data for training? So there it will, I think it could have an impact, but there it will definitely, due to lack of data, it will definitely need some sort of more inductive biases that we bake into models to bias them towards the specific use cases.
Thank you for the great talk. I think I saw a nice parallel between what you told us today and what we heard in the morning. So in the morning, we heard that you need AI engineers when you're doing like constraint optimization in the kind of the discrete domain of symbolic AI. And now you tell us that for your work you need to constrain the neural networks so that they adhere to physics, right? So is it the current state similar that you would say you need an expert to kind of to build this constraint to the neural network? Do you also see the similarity, or how far can you automatize this currently?
That's a good question. So it definitely is the case that we currently, no matter what domain we're working on, whether it's fusion or whether it's CFD or at Emmi or whatnot, we always have experts that tell us about the physics and what's important. Yeah, I mean, the thing is, like usually, if you assume that you have lots of data and you just throw all of the data into a model, then it sort of will approximate it. But the thing is that usually in those very particular scenarios, you don't have this much data. So I see it more as a spectrum with respect to data size. When you don't have that much data, you will definitely need an expert that give you some input on what physics you need to preserve. Yeah, the automating, I think this is maybe something that might inherently happen, but I still think that eventually you will need an expert eventually to look over it to verify that your trained model has actually captured it. And I mean, well, there you can probably automate to a certain extent, because it's for CFD, for example, it's known that you need to look at drag and lift coefficients for on an airplane and the surface pressure profiles. Like you can pre-compute this from a simulation. Don't need to ask an expert, but just compare it. But yeah, eventually, I'm not sure we'll ever be arrived there where we can really just throw everything in there and it will come out perfectly adhering to all the physics. Yeah.
Okay, so we would now be almost exactly in time plans, like unless there are really urgent burning questions, let's have a break. So
not as burning as a fusion plasma.
But first, let's thank Fabian again. So.